Now you saw in the inclusion-exclusion formula the term P, A and B, the chance that A and B both occur. And we are going to work out a way to calculate that with some natural ingredients at hand. And we'll do that first through an example. Here is something that you're going to get used to because you're going to see it over and over again. A box of tickets. There are many situations in probability that you can model by tickets being drawn at random from a box. For example, if you've got a die and you're rolling it and then you've got the numbers 1 through 6, you can just think equivalently of a box with 6 tickets in it, with the tickets that have the numbers 1 through 6 on them, and you pull 1, and that's like rolling a die. For now, I'm going to stick to a simple little box. 3 tickets, a red one, a green one, and a blue one. And here's another bit of language. 2 draws at random without replacement. What does that mean? That means you shuffle the 3 tickets, draw once, keep that ticket out, do not throw it back, without a replacement. So you have 2 tickets left in the box, shuffle those 2, pick one. And the question that I'm asking you is, what is the chance that you first draw the green ticket and then the red ticket? Yes, I know, some of you have done it in your heads already, but I want to examine what has been done. And the first thing we're going to note is that the chance of first drawing the green is 1/3. And so if I want to do that and as well want to do something else, then my final answer is going to be less than 1/3 because I am hard to please. I'm not satisfied with just the green. I want a red as well after that. Fine, so it's going to be less than 1/3. Well, how much is it going to be? And a great visual image to have is of these probabilities as long-run proportions. So just imagine a whole stadium full of people, each of whom is holding a box that contains these 3 tickets. And the deal is this. Each person draws 2 times without replacement. And the only people who get to stay and watch the game are those who got the green the first time and the R the second time. Everybody else has to go home. And the question we are asking here is equivalent to what proportion of people get to stay and watch the game? Well, so in the long run, what do you expect? Well, here's what's going on. At the first stage of the experiment, everybody draws from their box, and some people get to stay, and those are the people who pull out a green ticket, and everybody else gets to go home. So what proportion get to stay? Well, those are the people who drew a green ticket the first time. We knew that was 1/3, and this remaining 2/3, very sadly, gets to slink off. Fine, so now what? Do these people get to watch the game? Not quite yet. They have one more hoop to jump. They get to move to stage 2. And at stage 2, what must they do? Well, they must look at the box they've got, and not only do they have 2 tickets each, they have the same 2 colors. All of them in their box have blue and red. And they must draw from this and get a red. So what proportion of them are going to get a red? Half of them are going to get a red. And these are the eventual winners. And that's why this guy is so happy. The other half need to go home, and this person is upset. They nearly made it. But the second time around, Taiki messed them up. She should have picked their red card if they were to win, but she picked their blue card and they've got to go home. So who wins? Well, it's this fraction of people who win. And what fraction is that? Well, they are this half of the original 1/3 that won at the first stage. And so the winning proportion is 1/2 of 1/3. And as you recall, we had said that our overall answer is going to be less than 1/3. In fact, it's going to be a half of 1/3, a fraction of 1/3. And so yes, the answer is 1/6. We started out with a bunch of people, 1 out of 6 of them remains. So formally, what just happened? Well, so here's the problem again, and what we noted was the chance of first getting the green and then the red is 1/2 of 1/3, that is 1/6. Now, conventionally, this is written in chronological order. That is to say, the 1/3 first and then the 1/2 with the multiplication. And it is a good idea to note what these fractions represent. The 1/3 is clear. It is the chance of first drawing the green ticket. The 1/2 needs a little bit of discussion. It is the chance of drawing a red ticket, but only if you drew the green the first time. It is the conditional probability of drawing red the second time, given that green was drawn first. So it's a new kind of probability. It's not computed across all outcomes. It is computed across only those outcomes that had a green draw the first time. And so if we write this out in general, we get what is called the multiplication rule. And what is that for? Well, you've got two events and you're trying to find the chance that they both occur. A little bit of notation. You know the chance of A is just going to be written as P of A. The conditional chance of B, given that A has happened, is conventionally written this way. P of B, vertical bar, that is not a slash, vertical bar, A. And it is read P of B given A. The conditional probability of B given that A has happened. And so what's the rule? Well, the rule is to find the chance that A and B both occur, and it says take the chance of A and multiply it by the conditional chance of B given that A has happened. That works for all pairs of events on your set of outcomes. Now, I know some of you are thinking this, so I'm going to say this for now, but you're going to have to hold this thought. No, it doesn't matter which you call A and which you call B. You could as well write this as P of B times the chance of A given B. Now, conditional chances are easy to write down in what I call the forwards direction. You know what's happened at the first stage, you're trying to write down the chance at the second stage, usually you can write that down. But if you write the formula backwards, the ingredients are a little more complex, though they come out the same way. Hold that thought for a few lecture segments. We'll come back to it later. For now, if you want to find the chance that two events both occur, take the chance of the first one, multiply by the conditional chance of the second one, given that the first has happened. Let's run a couple of examples to make sure that we know what we're doing. What I'm going to do first is the same problem that we did, but I'm going to change the randomization. In our previous situation, we drew our tickets without replacement, but now I'm going to draw with replacement. What does that mean? Shuffle, draw once, note the color of the ticket, throw it back, draw again from 3 tickets, not 2. Same question, find the chance of first drawing the green and then the red. Alright, these two things both have to happen. So what are we going to do? Well, we are going to start out by saying, well, first we got to get the green. What's the chance of that? 1/3. Are we done? Nope. We want more, which means we're going to have a fraction of a fraction. So there's going to be a multiplication by a fraction. By what fraction? It's the conditional chance of getting a red the second time, given that you had a green the first time. Well, no matter what you had the first time, you're going to throw the ticket back. So the chance that you get a red the second time is, yep, 1/3. And so now the answer is not a 6th, but a 9th. And now you're in a position to move up from one card being dealt from a deck to more than one being dealt from a deck. So when we say cards, plural, dealt from a well-shuffled deck, what we are saying is that the cards are drawn at random without replacement. That's naturally when you deal a deck, you deal them one at a time. You don't throw a card back in the deck and deal it all over again. So here's a question. I'm going to deal 2 cards and I want the chance that the first is an ace and the second is a king. It's worth remembering what the deck looked like. There are 52 cards, of which 4 are aces and 4 are kings. So what is it that I want? I want first an ace, then a king. Alright, so the chance that I get an ace first is 4 in 52. Am I done? No, I want a king also. So I'm going to multiply by a fraction. What fraction is that? It's the conditional probability of getting a king given that you've already got an ace. Alright, so what's happened? Once you've got an ace, you have lost a card from your deck. So the total number of cards you have is 51. Of those, how many are kings? Well, you haven't lost a king. You still have 4 kings. So given that you took out an ace, the chance that you get a king is 4 in 51. And so there's your answer. The chance of getting an ace first and then a king is 4 in 52 times 4 in 51, and that is 0.6%. That is 0.6%. It's pretty small. While we're about it, let's just note that you can extend this to 3 cards, 4 cards, 5 cards. So if you deal 3 cards and you want the chance that all 3 are aces, then what do you do? Well, what's the chance that the first one is an ace? 4 in 52. Fine. So now what do we want? Are we done? Nope. We want the second one to be an ace as well. So we are going to multiply by what? By the conditional chance that the second card is an ace, given that the first one was. Well, the first one has been taken out of the deck, so now there are 51 cards left. And how many are aces? 3, that's right, because you've lost an ace the first time. This 3 in 51 is the conditional chance that the second card is an ace, given that the first one was an ace. Are we done? No! We're even more picky. We want yet another ace, so we have to multiply by what? That's right, 2 in 50. And what is this? This is the conditional chance that the third card is an ace, given that the first 2 were both aces. So if you imagine your stadium full of people, and they all have this deck of cards, the only people who get to stay are the people who deal 3 aces in a row. So at the first stage you have 4 in 52 remaining, at the second stage you have 3 in 51 of those 4 in 52, and at the final stage you have 2 in 50 of the previous proportion. And when you do the whole multiplication, that is a small number. 0.02 of 1%, actually it's 0.018 of 1%. It's a tiny, tiny number. If you're dealing 3 cards, please don't count on getting 3 aces. So what you've seen in these last 2 segments are a couple of simple rules. There's a plus rule and a times rule. And you have seen very small, straightforward applications of those rules. But what's interesting is that these rules can be combined in infinitely many ways to give you all kinds of very interesting probabilities without developing a whole lot more mathematics at all. And so now that you have the basic ingredients of probability, and you really do, the entire subject is based on these 2 rules, the plus rule and the times rule, used with increasing sophistication. And it is stunning. Wall Street works on it, all of statistics works on it, and it's just from 1 plus and 1 times. So in our small way, we will start examining what we can do with these 2 rules. And the next section will consist simply of a sequence of examples.